Okay, so chapter 8, we're going to be discussing gases. And what we're going to be looking at, first of all, is just generally where gases are found. So typically gases are things that are all around us. Right? For instance, the air around us is made up of a bunch of different gases. There's nitrogen, there's oxygen, there's CO2, carbon dioxide. And then there are also, we talked about in the periodic table, there are these noble gases that belong to group 8. So things like helium, neon, argon, etc. So they're very common, in other words. When it comes to the behavior of gases, there's a theory that we use in chemistry that describes how gases behave, and we can use it to predict how they're going to behave as well when conditions change. And that's called the kinetic molecular theory, which is often abbreviated as KMT. And according to this theory, the particles of a gas are in constant random motion. So that's where the term kinetic comes from, right? They're always moving around constantly and randomly as well. In terms of their attraction, there's very little attractive or repulsive forces between the particles. In terms of the proximity of the particles to each other, they are very far apart, right? And we saw that when we looked at the differences between solids, liquids, and gases earlier on in the semester. So the particles are very far apart from each other. And this would then mean that there is lots of space between them relative to or compared to the size of the gas particles themselves. Okay, so the thing to keep in mind with this one is that the particles are extremely tiny. Right, so even though they may be molecules like oxygen or even atoms like neon, they are extremely small compared to the space that they occupy. And then we can say then that the volume of a gas is simply equal to the volume of the container that it occupies. So in other words, a gas expands to fill the volume of the container that it is held in. The very last part of the kinetic molecular theory addresses the kinetic energy of the gas particles, and what we can say is that the kinetic energy increases as the temperature of the gas increases. Right, so in other words, as you increase the temperature, the particles are going to have more motion. They're going to be moving around more frequently with more energy. There are 4 properties that are going to describe a gas, and this is what we'll be focusing on in the subsequent sections. So the first property is called pressure. Pressure is abbreviated P, big P. The second is the volume, which is abbreviated big V. The third is temperature, which is abbreviated big T. And then the fourth is the amount, which is abbreviated small n. And each of these are going to have different units associated with them. And some of these we've seen before. So volume, remember, is just the amount of space occupied by the gas. And the typical units that we're going to see would be liters or milliliters in some cases. For temperature, right, a measure of the average kinetic energy of a sample For gases, you want to make sure that this temperature is, or it must be in Kelvin. And you want to make sure that you do that conversion before you start doing any sort of calculation. Turn it into Kelvin at the very beginning. And then the amount is typically in number of moles. So the one that we haven't seen before or talked about is the first one, which is pressure. Right? So what is pressure and how does pressure actually arise? Well, we actually define pressure as a measure of the force acting on some sort of an area. So force over area is what pressure is equal to. So if you think of, if you have a container with a bunch of gas particles in it, right, these gas particles are going to be moving around, zipping around with a great deal of energy. Then eventually they're going to hit the walls of the container. Right here, for instance. So when they hit the wall of the container, they will exert a force on that area, which is what pressure actually is. The most common units that we're going to see for pressure in this class are atmospheres, which is abbreviated ATM. We're going to see mmHg, which stands for millimeters of mercury. And then we're also going to see torr as another unit. And the relationship between them is pretty simple. 1 atmosphere, 1 ATM is equal to 760 millimeters of mercury. And also 1 atmosphere of pressure is equal to 760 torr. So there's a device that we use to measure pressure. It's called a barometer. And the way that it works is actually quite simple. We have here a container that has some mercury in it. We take a long thin tube, open at one end, and we invert it into that liquid mercury. The atmosphere, the gases of the atmosphere actually press down on the mercury and they force the mercury up into that tube. We can actually measure the distance from the base here of the tube to the top of the tube, and we see under normal conditions at sea level, right, that distance ends up being 760 millimeters, and it's mercury that we're measuring, right? So that's where the unit actually comes from. So if you were standing at the surface of the planet at sea level, let's say that was the surface of the planet and you were standing here, and then this was the top of the atmosphere, right, you would actually experience 1 atmosphere of pressure due to that column of air above you from the top of your head to the top of the atmosphere pressing down on you. So if you were to change your elevation, for instance, if you were to climb a mountain, you're at the top of this mountain, right, and that column of air above you from the top of your head to the top of the atmosphere actually shrinks. So because there's less air the higher up you go, the pressure here is lower. Compared to if you were standing at sea level. Alright, so what that means is, as you change your elevation, as you go higher and higher up in altitude, the pressure actually decreases. And we can see that if we make a comparison. If you look at sea level, the atmospheric pressure is 760 millimeters of mercury. If you were to go to Denver, Colorado, which is a mile high, you see that the pressure decreases to 630 millimeters of mercury. So we can say as elevation increases, atmospheric pressure decreases. Okay, now we're going to take a look at some of the relationships between the properties that we looked at previously. and we're going to be looking at the relationship between two of these properties at a time, which means that we're going to keep the other two properties that we're not focusing on. We're not going to change those. So in other words, we're going to keep those constant. So the first relationship we're going to take a look at is the relationship between pressure and volume, and the other two properties, temperature and amount, we're going to keep those constant, meaning they're going to be unchanged. And when we look at the relationship between pressure and volume, what we actually find is that P and V are inversely related. So what that means is that as one goes up, as pressure increases, the volume does the opposite. It decreases. Or we can say, as pressure decreases, the volume will increase, right? So it's kind of like a seesaw relationship. That's called an inverse relationship. So the way that that works for us in terms of how we're able to use it to solve problems, mathematical problems, is as follows. If we multiply the pressure times the volume that we start with, and we're going to abbreviate that as P1, V1, these are our initial conditions. Whatever value we get should be equal to the final pressure times the final volume, which we abbreviate P2 and V2. So those are our final conditions, right? That's mathematically how this relationship can be expressed. And by the way, this is called Boyles Law, right? For simplicity's sake, sometimes you'll see the multiplication sign omitted. So we'll see P1 V1 is equal to P2 V2. And we can use that relationship to solve some problems. So let's take a look at one example of where we can see that. All right, so let's say we have here a sample of argon gas, and it's at a pressure of 0.50 atm. So with these gas law problems, they tend to be word problems, and you have to extract the information that's needed. So let's just write down what we're given. We're told that we have a pressure of 0.50 atm. So P is equal to 0.50 atmospheres. And it says that it occupies a volume, so V is equal to 1.25 liters. And it's asking us to find, well, what would be the new volume? So some sort of a V is what we're trying to find if the pressure is increased to 1.48. So a new pressure is 1.48 atmospheres. Okay, so based on the information given, we can now properly depict what those different conditions are. So 0.50 is going to be what we're starting with. That's our P1. 1.25 liters is our V1. Those are our initial conditions. And the 1.48 atmospheres is our final pressure, and our final volume is what we need to find. And we're told at the end here that the temperature and amount are held constant. So what that means is that we need to look at the relationship between pressure and volume. So we're going to use P1 V1 is equal to P2 V2. And what we don't know is V2. So we need to solve this for V2. And what we can do to isolate V2 on one side is we can divide it by P2 to get rid of it from the right side. So P2 goes away. Whatever we do to the right side, we have to do to the left side. So we divide the left side by P2 as well. So we end up with V2 is equal to P1 times V1 over P2. And we know what those values are because we were able to pull it out from the equation, right? We know that our P1 is 0.50 atmospheres. We know that our V1 is 1.25 liters. And we know that our P2 is 1.48 atmospheres. So I'm not just putting in my numbers, I'm also putting in the units. So I can see that the units atmospheres cancel, and I end up with liters as my unit, which makes sense because I'm trying to find volume. And all I would need to do would be to stick that in your calculator. And then that gives 0.42 liters as my final volume, right? So we said that the unit makes sense, and now the number actually makes sense as well, because we know for an inverse relationship, as we increase the pressure, the volume should decrease, and it did. It went from 1.25 down to 0.42 liters. Okay, now we're going to take a look at another relationship between two properties. We're going to look here at the temperature and volume. So the VT relationship. And if we're looking at the relationship between V and T, that means we're going to keep the other two, which are pressure and amount. We're going to keep those constant. All right, and the relationship between V and T is a different one than between pressure and volume. We say that V and T are directly related. So what that means is, as volume goes down, the same thing happens to the temperature, or as volume increases, the temperature will increase as well. Mathematically, we can represent that as follows. We can say V1 over T1 is equal to V2 over T2. Right? And that's how this relationship between V and T is useful to us. This is called Boyles Law. So if we look at an example of where we can apply that, it says here a sample of argon is at a temperature of 21 degrees Celsius. So again, just like the first one, let's just write down what's given. So T is equal to 21 degrees Celsius. So you'll notice here that temperature is provided in Celsius. Before you go any further, you want to convert that to Kelvin right away. So we're going to add 273 to it. That gives 294 Kelvin. And that's the temperature that we're starting with. So that's T1. And it occupies a volume, V1, of 0.20 liters. What would be the new volume? So the new volume implies that V2 is what we don't know. If the temperature is increased to 33, so our final temperature is 33 degrees C, convert that to Kelvin. So that gives 306 Kelvin. And we're told here that the pressure and amount are constant. So that means we're going to use V1 over T1 equals V2 over T2. Our unknown here is our V2, so we need to solve for V2. And to isolate it on one side, what we can do is we need to get rid of the T2. So we can multiply the right side here by T2 to cancel it out, which means we need to multiply the left side by T2 as well. So then all that's left to do would be to substitute our values, right? So our V2 would be equal to our T2, which is 306 Kelvin, times V1, which is 0.20 liters, divided by T1, which is 294 Kelvin. So kelvins go away, we end up with liters as the unit. That makes sense. I'm trying to find volume, so stick that in your calculator, and it gives 0.21 liters, right? So in terms of the units, it makes sense, we have liters. And in terms of the number now, right, because there's a direct relationship between V and T, if I increase the temperature, the volume should increase as well. And it did go up, not by a lot, but it did increase. So the final answer does make sense. So the next relationship we'll take a look at is the relationship between temperature and pressure. So if we're looking at the PT relationship, that means we're going to keep the other two variables, which would be volume and amount, we're going to keep those constant. And the PT relationship is one that's similar to the VT relationship. In other words, P and T are also directly related. So in other words, as pressure goes up, the temperature goes up, or as pressure goes down, the temperature goes down. All right, and we can express this mathematically, just like we did the VT relationship. P1 over T1 is equal to P2 over T2. We can use that to solve our gas laws or gas problems that contain pressure and temperature in it. The one thing you want to keep in mind, though, is that temperature needs to be in Kelvin. Before using the equation. Okay, and then the next gas law is the relationship between volume and amount. So we're looking here at the V and N relationship, which means we're going to keep the other two, pressure and temperature, we're going to keep those constant. And the V and N relationship is also a direct one. So V and N are directly related. Which again means as V goes up, N goes up, or as V goes down, N goes down. Right, and similarly, just like with the other direct relationships, we can express this mathematically. It's my initial volume divided by my initial amount is equal to my final volume divided by my final amount. And this relationship is called Avogadro's law, named after Avogadro. So one of the consequences of the VN relationship is we can actually use some aspects of it to compare gases, compare all sorts of different gases under similar conditions. And the conditions that we're going to use to compare our gases are known as standard temperature and pressure, which we abbreviate as STP. So the standard temperature corresponds to 0 degrees Celsius, which is 273 Kelvin, and the standard pressure is 1 atmosphere. And what we find is that it doesn't matter what gas you have. 1 mole of any gas under STP conditions occupies the same volume, which is 22.4 liters. So we call that the molar volume under those conditions. So we can say 1 mole of a gas then is equal to 22.4 liters. So we can take that and we can turn it into 2 different conversion factors that will allow us to convert between liters and moles of a gas. So here's an example of where we may encounter the molar volume, and this may seem like a fairly simple question in terms of, or concise questions in terms of the length, but it may be a question where you may not even know where to start with it. So as with the other questions, we saw that we were able to pull out some information, and there were clues in it that told us what relationships we would want to use. We're also going to see similar things happening in this problem. So it asks us what volume will 4.00 grams of CH4 by the way is a gas, it's methane, will occupy under conditions of STP. So the STP here is your clue that we're going to be looking at molar volume. Right, because we just defined under STP conditions that 1 mole of a gas should occupy 22.4 liters. So 1 mole of CH4 should be 22.4 liters. We are asked to calculate volume. We don't know what that is. What are we given? We're given the grams of methane. So if I want to use my molar volume, I would first of all need to convert my grams of methane to moles of CH4, and then when I get to moles of CH4, I can then use my molar volume over here to convert my moles into liters of CH4. How do I get from grams to moles? Well, I'm going to use the molar mass, which you've done multiple times already. Right, so you can calculate the molar mass of CH4 by adding together 1 C and 4 H's, convert your grams to moles, and then use the molar volume to convert the moles into liters. So this is just another example of where you're using dimensional analysis to simply convert units, right, which is something you've done ever since week 2 of the quarter. Okay, and then the last law we'll take a look at is called Dalton's Law of Partial Pressures. In order to explain this, we need to first of all define what partial pressure is. So partial pressure we can define as the pressure that a gas from a mixture of gases would exert if it were by itself. And the way that Dalton's law of partial pressures work is actually quite simple. If you can add, you can do this. So it goes as follows. It says the total pressure of a mixture of gases is the sum of the individual partial pressures. So in other words, the total pressure PT is equal to the sum of the partial pressures of all the different gases. So this here would be the pressure of first gas, whatever that is, plus the pressure of the second, plus the pressure of the third, etc., until you've accounted for all of those gases. Right? The only thing about you need to pay attention to with the Dalton's law of partial pressures is you want to make sure that all of the pressures are in the same unit, so you can add them together properly. Okay, so convert them all to atmospheres if you need to, or convert them all to millimeters of mercury if you need to, but you just want to make sure that they're all in the same unit of pressure.